Hello, Judy. 안녕. 방학은 잘 재밌었어? 잘 쉬었어? 아이고. Yes, we're back. 시험을 그때 마지막에 봐가지고 뭐 어떻게 봤는지 물어볼 게 없었었는데. 오케이. 응? 어려웠어? 뭐 모르는 문제 나왔어? 어떤 게 나왔니? 그치, 그럴만도 하지. 점수는 아직 안 나왔고. 다 어려웠을 거야. 우선은. 그래서 그러긴 한데 그래서 조금 거기서 앞서갈 수 있으면 좋긴 하거든. 그래서 보자. 나오는 거. 오케이. 그래서 모듈 에잇을 할 수도 있어. 진짜 왔다 갔다 한다. 그래도 다행인 건 모듈 5 우리가 여기서 한번 했기 때문에 무슨 말인지 알아듣거나 진도 나가는 건 문제 없을 건데 뭐였었지? 뎁스터리가 뭐 했을 텐데 시험 봤던 거를 기억하거든. 또 시험 같은 걸로 문제 있으면 알려줄게. 얘기해주고 뭐 연습 필요하면 더 얘기를 하면 되는 거니까. 오늘은 starting 6 homework. 아마 모듈 7은 우리가 이번 텀 1 중간 정도 시작을 한 번 더 할 거야. 그래서 쭉 한번 갈 거니까 그때 한번 해보고. 근데 어려워. 계속 반복하는 수밖에 없어 그건. 오케이. 시간이 있으니까 조금. Morning, Maureen.
Morning.
Okay.
Your book?
Yeah, the history. Oh yeah. Degrees in Korea. Daddy's in Korea. Joanne's. Exciting. Okay. Should be. Oh, yeah. Okay. Okay, how's everyone? Year 12, term 1 starting in a few weeks. Stressful, okay. Actually, you have the module 5 test coming, term 1. Yeah, so probably give you some more practice papers to do. Yeah. And some of the contents we're covering today and next week, which is about the KA calculations, it's not going to be in your exam, but it will be helpful to understand what the K is again. All right, the plan is try to finish all the modules, maybe like most of the module 6 by this holiday, so that we can more focus on doing the pracs, titrations. So titration will be in probably in the first week of your back to school. But before we perform the prac, you really need to understand what the acid and base and reactions are, and you need to do like the calculations based on too. So calculation is something that very, very, very important in the recent HSC. Did I share the last year's HSC paper, or like did I show you that what questions you had in module 5? Okay, so module 5 and 6, I picked the module 5 and 6 the most difficult out of the whole year 12 because we never know what type of calculation questions you would get. Like it's getting really complicated. You need to really think and explore it, and you need to just go think deep into it. So you need to practice some of the basic questions first. Okay, all right, let's start. I'm not too sure what happened to Joanne. Okay, hopefully. All right, we have some module 6. This is a kind of continuation from the module 5, which is about, we learned about dynamic equilibrium. I'm not going to spend too much time on the dynamic equilibrium, but as this is the first day back, it might be a good idea, like just revising that what we learned about dynamic equilibrium, because it's been a while, it's been a month. Okay, so we learned about dynamic, or sometimes known as chemical equilibrium, that we need to have a few conditions for to achieve that dynamic equilibrium. One was you must have some reversible. It must be reversible. If the reaction is not reversible, then we can't have the dynamic equilibrium. And at the equilibrium state, we know that the concentration of the reactants and the products are constant. They remain constant, as in like they do not really change due to the same rate of the reaction rate. Okay, so those are the 3 conditions that you have to understand. You have to and I showed you probably like last year when we started module 5 beaker example, demonstrations. You can possibly have some modeling questions quite a lot these days too. So she's asking you, hey, we're modeling some dynamic equilibrium. One of the good example was, I've been saying quite a lot, going down escalators, you try to go up, okay? You're working really hard to achieve the equilibrium state, which is remain this constant or the steady state. So that's how we define our dynamic equilibrium. Of course, we learned about Le Chatelier's principle too. Okay, all of you here, I know that you have the fine definitions of the Le Chatelier principle by now too. So yes, you need to memorize it, and this is the point that you need to mention that, otherwise you will lose a mark, but you won't get the extra mark by just defining the Le Chatelier principles. Okay, and we talked about some changes throughout the reactions. So that we have a change in the concentrations, change in the pressure, change in the temperature, especially the temperature. We dealt quite a lot about the temperature. Okay, that depends on the excellent endothermic. It will make a shift. Also, the increasing temperature would increase the rate of reaction for both sides. So, if any of you like writing reports coming to module 5 or like having exams related to module 5, I'm taking the one. Temperature is definitely the one that you will get the exams about, like questions about. Okay, so after that, we went through something more about. Anyone remember the Le Chatelier principle? We did about KEQ. Okay, I hope you remember the KEQ is simply the K is the constant at the equilibrium, showing that the ratio between products on the reactant. So that we have to interpret that as higher K means that we have a lots of the reactant products remained, or like in the constant the concentrations. Lower K means that we have a certain like really small amount of the reactants remained. So that is something that's very important. This is related to today's calculation related to the K calculation of the acid reactions. Okay, again, I'm gonna bring up some of the dynamic equilibrium concepts so that you get to know like how we're gonna relate to the module 5 and 6 together. What else? After we did some KE, we also learned about KSP. This is the part that I know you make like SP, the solubility product, other thing. The key word for the solubility or solubility product is always be up to. Remember, like the KSP is still the same as the K. We use the same method to find the KSP as like find the KEQ, but it's not the exactly same as the KEQ contents too. I know this is things like make you feel miserable, okay, some dreadful, but if you remember, the solubility is all about up to how many things, how many grams, up to how many moles we can dissolve in the liter. That's a fixed. That's a fixed. We can't change that, the solubility. This is something that's very important. Salt have a very certain solubility. We can't change it because it is what it is. They are born with that. They are made with those chemical properties. So this is a key point of the understanding the solubility products. Once you get it, then you probably know what I mean by KSP better. And we had to deal with some other questions about QSP that, when in the case we have a greater QSP than KSP, whether like in a precipitate will form or not too. This is all about whether we get the oversaturated situation or the undersaturated situations too. So hope you remember that. Like, I hope I want you to remember that the KSP means that it's at the saturation level. They can't dissolve furthermore. Okay, and this gives you try to challenge that, understand the point as you go, because this is coming out again and again and again, not only for the module 6 or for the module 5 later on too. Okay, welcome. So quick revision on the module 5. Now let's move on to the module 6 today. And as I said, I'm going to relate to some of the module 5 contents to the module 6 in chapter 2 more likely. So module 6 is all about acid and base reactions. So those of you who learned, or like those of you like everyone did the chemistry in year 10, we did a little bit about acid and base in year 10. And asked my student to memorize some of the templates for the acid and base reactions. If you don't, if there's a chance, you probably know what the kind of the products are like between acid and base. Probably this is a good time to memorize that again. Oh, don't have a black. Okay, never mind. Grab some black in a second. So let's quickly talk about what acid and base we understand up to now. Okay, when I say acid in chemistry, I'm generally dealing with something related to something like having the hydrogen ion. Okay, now H plus is known to be a hydrogen not the atom. I want you to realize that the H plus indicates that it's the ionized state. Means that it's simply hydrogen ion, which is equivalent to the proton itself too. Because hydrogen is only the number one element or atom that has only one proton inside. Okay, so having the plus means that it lost electrons somehow. So as is something they're dealing with the hydrogen ions, because we know that some example of the acid, there are HCl. Okay, you probably have seen that before. We kind of pronounce it as hydrochloric acid. We don't really say it hydrogen chloride. H2SO4, you probably have seen that before. It's called the sulfuric acid. I can write it here, hydrochloric acid. This is known as sulfuric acid. We also have HNO3, that's known as the nitric acid. H2CO3, known to be carbonic acid. You don't have to write it down. It's all given on your page, the next two. So what else we have? Oh, we have also have this H3PO4, known to phosphoric acid. We also have CH3COOH. Okay, this is also known as acetic acid. Also something known as ethanoic acid in the module 7 in the organic chemistry. You will now we'll probably learn why we write in the CH3COO from the module 7. Okay, we just leave that for acetic acid for now in here. What you see in common between all the acids that we say in the chemistry is they have hydrogen ions in common. Okay, so we gotta think about, you gotta do something about hydrogen ion. And if you think about the property of the hydrogen ion, acid and base reaction kind of makes sense better. So let's have a look at some of the pages there. We have page 2. It shows all the common acids that we use in the everyday uses. So given hydrochloric acid, HCl, we have actually carry some hydrochloric acid in your stomach. It's kind of helping to digest the foods. Okay, so that's why when you get a reflux, you get some kind of burning sensation due to the hydrochloric acid. Sulfuric acid, H2SO4, it's kind of commonly used, something that we use for the oven cleaner or car batteries. Okay, HNO3 is commonly used in the fertilizers, dyes, and explosives. Ethanoic acid, vinegar is simply the ethanoic acid, or in the acetic acid. Carbonic acid, we have in the soft drinks. Yes, we have a slight bit of acid in your Coca-Cola, Fanta, or even carbonized water. Phosphoric acid in the flavoring. Citric acid, yes, that's a sour taste of your fruit or your foods. And ascorbic acid, which is known as vitamin C, is also known to be an acid type too. Okay, so we have a various type of that. Now, what you need to memorize here is at least these on the list. You need to memorize at least those in terms of their chemical formulas. And they're not too complicated, to be honest, because I'll ask you to memorize all that sulfate, nitrate, carbonate, phosphate, and even acetate. We just need to simply add a hydrogen ion that makes the acid. Okay, so at least how many? 1, 2, 3, 4, 5, 6. At least 6. You do not really need to memorize citric acid yet. Okay, there are some times we get the questions about citric acid. We just need to know this is having many hydrogen ions in it, but most likely you will be given the chemical formulas. Same for the vitamin C. So only 6 of those something you need to memorize for up to now. Okay, now, then how do we know those are acids? Because all those acids have a very common property, the physical property of when you taste them, they taste sour. But you dare not to try to taste the sulfuric acid. You dare not to put some drops of the hydrochloric acid on your tongue because, as I said, you get a very burning sensation when you get reflux. And imagine that you're putting that in your tongue, putting your finger. What you get is, you get this. They are please remember that they are highly corrosive. They are highly corrosive. This is a term that you have to use for the safety precaution. Because you get a lot of the questions about, hey, what's the safety precaution dealing with the acid? Don't just say, oh, they are dangerous. They're not explosive. They are corrosive, which means you actually get a huge severe skin damage. This is due to the hydrochloric acid spillage. Okay, and this is the reason why, because they are highly corrosive. You need to wear the PPE, including safety gloves, okay, lab coats, closed shoes, in case of some of the spillage, goggles, okay, mask. Sometimes it depends on the case. It depends on what kind of experiment you do. Okay, please remember that. So these are the consequences of not wearing the any of the acid. Now, unlike the acid, we have a few different type of bases there. So let's talk about base. Something we're revising some of the module year 10 contents. We have a few different type of bases unlike the acid. We can have a base with combined with the OH minus. This is called the hydroxide ion. We can also have the base is made with the carbonate, CO3, 2 minus. So carbonate is something that's very interesting because when you combine with the hydrogen, it forms acid, but we also have something with sodium carbonate, for example. So this is a carbonate. Similarly, you can also have hydrogen carbonate. It's combined together. This is called the hydrogen carbonate. In common name, it's known as bicarbonate. So if you haven't seen the sodium bicarbonate in you can actually buy the Woolies, Aldi, used for like cleaning detergents. Yeah, they are made with the hydrogen carbonate. Sometimes they are made with the oxide, O2 minus. So we have a 3 type of bases. And we're going to learn about why we deal those at the bases, how we define the bases then. Okay. So example of the sodium, the base made with the hydroxide, we know that many sodium hydroxide. You have seen that quite a lot. I have to use purple. Sodium hydroxide, the sodium hydroxide. Any of them made with the calcium hydroxide is working as calcium hydroxide. They are working as a base. And the common use of the sodium hydroxide is known to be drain and oven cleaners. So they are also known to be highly corrosive because you dare not to touch the oven cleaner with your bare hands. If you ever touching, or the bleach is a good example. Okay, bleach is kind of like bleaching all your colors of the clothes. Imagine that you spill that on your skins, you get the a huge amount of skin damage. It's not causing that death, to be honest, but it's quite hurt. Okay, all right. Carbonate examples: we have a sodium carbonate. We also have a sodium bicarbonate or sodium hydrogen carbonate. Okay, now some of the oxides are working as a base. So, for example, sodium oxide. All the oxide combined with the oxygen combined with the some transition metals that can be working as the base as well too. Exception is this: we also have NH3, which is called ammonia. Ammonia is not like belong to any of the categories given over here, okay? But still working as a base somehow. And we're gonna learn about why is working as a base. I mean, why do we define that ammonia as a base, even though it does not have any of the hydroxide, carbonate, or oxide in it? Okay, so those are the common examples of the bases that we commonly use. As you can see, like sodium hydroxide, ammonia, calcium hydroxide, magnesium hydroxide, sodium carbonate is given. Okay. But some of those are known to be not that toxic, not that corrosive. For example, sodium bicarbonate, as I said, commonly get it. We can actually consume some of this bit of the sodium bicarbonate. We use that to wash the fruits, get rid of fertilizers. But some of those, you never imagine to put it sodium hydroxide in your mouth because they are highly corrosive. So there must be some difference between the chemical properties as well too. All right. So to understand the acid and base properties, naming acid, let's not worry about this. Naming bases, they are pretty easy. So we're going to move on to the next page, which is page 8, please. So instead of we using something like a tasting, like, yeah, guys, one thing. You never, ever, ever use your body parts, any of the body, to test for the acid and base. Because generally, bases are kind of soapy and slippery, generally. But it doesn't mean that you touch it, you feel that texture to see the figure out, oh, this is a base because it's slippery. Okay? You never taste the acid, as I said, to test like go for the sourness. Taste the base, by the way, is a bitter. If you ever taste like a chew, like a soap, yeah, that's the taste of the base. But we never do it in chemistry. So this is the reason why we need to use something that's very special to test for the acid and base. That is known as the indicators. Okay, so indicators, or in general saying that acid and base indicators are the one that were helping us to test for whether they are acid or base, or testing for like their extra pH levels too. And out of many in here, you actually need to memorize all that tables. Memorizing, you need to memorize the name of the indicators, you need to memorize the pH ranges of them, you need to know that colors of the color changes too. So for example, in our like titration experiment, we probably did we kind of did the titration before here. We use indicator called the phenolphthalein. I know this sounds like it's hard to pronounce it. So the way you can do it is phenolphthalein is how you need to pronounce. Okay, phenolphthalein is how you need to pronounce the chemicals. Just you need a bit like a tongue practice to get the pronounce about, but spelling is very important. Okay, did you and I think we all saw that the color was started with the colorless. As we adding some bases to it, turns to the bright pink color. Does everyone remember that? We have an indicator goes like a really pretty hot pink color. That's a pink color of that, and that indicates that it's now reaching the pH at 9. Okay, so when we get the pH range, they are started turning and change the color. Okay, so I give you some more like a chart of that later on. I have maybe a print of the pH indicators so that it's helping you to memorize it. Take your time to memorize all the pH ranges and those acid and base, because sometimes in the multiple choice, they're just simply giving you, hey, we have a pH of 9. What would be the suitable indicator to design for the titration? They don't tell you any of the pH ranges. They won't tell you any of the color changes. So it is the pre-assumed knowledge that you need to memorize some of the pH changes. So the easiest way to memorize is I'm starting from this something detecting analyzing the acid first. So methyl orange has a pH range of 4 to 6, means that it changed the color in the 4 to 6. So if you remember that pH 7 is a neutral, below the pH 7 is something we call as acid. Above the pH 7 is known to be a base. So 4 to 6, especially 4, is testing for something known as a more acidic part. And you'll see that the color is changing from the orange to yellow. Does it make sense? You will start to see like an orange color as is from the name methyl orange. When you're getting increased the pH from the orange color, it's going up at the pH of 4 to 6, it changes the color to the yellow. So what I mean is up to pH 4, the color shows the orange. After 4 to 6, it shows the color of the yellow in 4 to 6. Start turning, change the color to the orange. Sorry, to the yellow. And it will remain as a yellow as you go. All right. Same for the bromophenol blue, or sometimes we use bromothiamine blue. It has a pH range of 6 to 7. Means that prior to pH 6 or 7, it shows up to pH 6. It shows the color of the yellow. Now, when it hits the pH of 6 by putting some more acid, it takes to change the color to the blue. Does it make sense? Okay. Same for the thiamine blue. Up to pH 8, it shows the color of the yellow. Then once it hits the 8, it started turning the color to the blue. So that's the indication that, oh, this is like, so we have now a situation that where the pH is slightly above the 8. So it kind of indicates the quantitative pH changes as well too. Phenolphthalein, we talked about it, colorless before the prior to the pH 9 and started turning to pink. And the alizaline yellow, 10 to 12, is testing for the more higher pH, up to 10. Unfortunately, I don't have many of the indicators in my lab. I only have phenolphthalein and some of the bromothiamine blue or thiamine blues, okay, and some universal indicators. In schools, when you're going back to school and you're learning about module 6, you probably need like to do some practicals about using different indicators, maybe, yeah. But that's could be a good chance to memorize those, pH changes and the colors again. All right, any questions about indicators? So this is a very useful tool so that we do not need to think about, to think about like tasting the acid to test for their pH. We simply need to do, just put some methyl orange and we can test for some acid. But do you think it'll be suitable using the phenolphthalein to test for the acid? It would not be a good choice because the phenolphthalein would not change the color up to pH of 9. Acid is known to pH below 7. So you won't ever get the pH changes, or the color changes using the phenolphthalein for the acid. This is what I mean by you need to choose the suitable indicators for the very specific experiment on acid and base reactions. Later on, we're going to talk more about titrations, and the inside titration we're going to learn about something known as equivalence point. Okay, in that, I'm going to explain you once more that why we need to memorize those colors and choose the suitable indicator for that practical that kind of practicals. Okay, the things that we're going to miss out is we're going to miss out to making the natural indicator using the red cabbage. That this is kind of old-fashioned way we made it. So some of the plants are actually having some very specific, like the dyes, the colors that's sensitive to the pH changes. So if you ever seen that, if you ever done like some kind of, I would actually call like a biology lab in my freezer that leaving the foods are too much and see like it's a fungi living there, okay? Or if you ever seen like a red cabbage left it in your fridge for a really long period, it started turning the color change to like sluggish blue or yellowish too. Okay, I know it sounds gross and disgusting too, but because of some of the especially blue or like red, the plant, for example, beetroots, blueberries, red cabbages, those are the ones that are very sensitive to the color changes. The pH changes. So when you use the red cabbage indicator, page 11, it shows you that depends on the pH of the your solution you're testing. The red cabbage solutions, or maybe the solution that we kind of boil the red cabbage water, can change the color quite differently. So pH 7, it shows the color of the blue, but in the pH 2, which is highly acidic, it shows the color of the red. pH of the 11, which is highly basic, this shows the color of the kind of yellowish green. So this is how we actually make this something known as the universal indicator. Okay, the reason why we call the name that a universal indicator is because we are able to use that universal indicator for both acid and base from the range of the pH 2 to pH 11 or some of the pH 1 to pH 14. Okay, so this is things that we actually use to make it. Sometimes we use the demonstrations, but we're not going to do it as I'm going to want to more focus on to the titration later on. Okay, so but if you have a chance to make the red cabbage indicators in schools, you probably do. I believe like some of the schools actually did it last year, so you probably do that too. It's a good chance to think about why we're doing it. The only reason why we're doing that is we want to determine the acid and base without touching, without tasting, without like spilling it. Any questions up to here? Okay, all right. Let's move on to then the real definition of the acid and base. I'm going to introduce a little bit of the historical background of the acid and bases, that why, how, where we started from, what is acid, what is a base. Everything started from the person called Lavoisier. Okay, and the first time he thought about, he was the pioneer of the chemistry. He actually tested quite a lot of the chemicals. Oh, by the way, I just give you the most important point. You just need to memorize that, like, their achievements, and you also need to know about their limitations, because science or theory is developed from one theory's limitation to like an develop from to like an investigate limitation. It develop into new theories. So it is very important to know a person's like achievements and the limitations, and move on to the next, and goes on. So for the Lavoisier, he first thought like an acid is something that contains the oxygen. So why is that? Because he thought like he was commonly held belief, okay? Because he studied about the phosphorus and the sulfur combustions, and from then he found that something very interesting happening. That they combine with something in the atmosphere, and he observed that when dissolving the water, the phosphorus and sulfur oxide made acidic solutions. So without testing with like he probably used the indicator. He probably used like a taster a little bit too. He probably see like after they combusted the phosphorus and sulfur. Those of you who study about like a little bit moisture age, maybe not, okay? Combusting the sulfur and phosphate, actually making the sulfate and sulfate and phosphate. And that combined with the water means they're actually making some of this sulfuric acid and phosphoric acid, which means he actually found that how to produce a sulfuric acid. Okay, and he kind of tasted it and put it into the indicator, saying, oh, it's changed the colors. And they all have sharing the same changes in colors. So that's kind of indicate that, oh, that's the acid. So he only believed that it is something that combined with the oxygen. It's going to deal with the oxygen. So for the Lavoisier, I'm going to write it down. Let's start with the case, Lavoisier. So definitions, first of all, he believed that is something, acid is oxygen contained. That's the first thing he believed so. But the limitation is there are some other acids without having the oxygen. Okay, there are many acids without the presence of the oxygen. So that's a limitation. Okay, so he was not able to say like, why we get like some of the acid that's not really having the oxygen either too. So this means that we need to develop this. We need to kind of investigate this limitation to develop into the next theory that proposed by Davy. Now Davy's experiment, Davy's like the definition is more scientific, because he actually improved the limitation of the Lavoisier, saying, oh, acid is something going to deal with not only the oxygen. He believed that acid is something dealing with the hydrogen. It's also given in here. So Lavoisier believed that oxygen was present in the nitric acid, and okay, it's too much information here. So there we go. Third point, Davy defined the acid as some compound which contains the element hydrogens that could be replaced by the reaction with a metal. So this is what we have actually performed in the year 10. You put a little bit of the acid to the metals and seeing that there's a bubbles. And he believed that, anything that produced that type of bubbles with the metal reaction, that is an acid. And when he saw that, that's all contained that of the hydrogen. So it is about hydrogen contained. And also he believed that it produced hydrogen gas with metal reaction. That is a definition of Davy's acid. Okay? So after that, he kind of described it, and he kind of further investigated into the neutralization. So this is where he comes to the neutralization comes along. that when acid and base are mixed together, it produces salt and the water. You probably have learned that as a template of the chemical reactions. So he was the first one actually perform the chemical experiment, okay, on the investigation to figure out what the acids are. So he was quite successful in terms of that. But the limitation is quite obvious too. It's not that. It's not all acid. Okay, not all acid. Okay, sorry, like some, many, I should not say some, many of hydrogen contained compound are not acid. For example, NH3. This contains hydrogen, but it does not working as an acid. Okay, so it doesn't like hydrogen is not essential to have be an acid. It would be essential, but not all that hydrogen contained compound is working as an acid too. So this was remain as his limitation too. Okay, so to develop, I mean, accepting the Davies achievement there, we're still accepting that even now. We still believe that, yes, an acid and base reacting, producing salt and water, we still trust that. Okay, we still investigate it. So it becomes more like a theorem in nowadays. So to develop these ideas, the person called the Arrhenius, this is someone that very, very, very important. Spelling double R, Arrhenius. He kind of redefined the acid from the Davies. He kind of developed it. So what he believed that is acid is not the hydrogen, it is hydrogen ion contained. That is H plus. So I hope you see like a difference between Davies definitions. He only said anything with the hydrogen, but Arrhenius is the one that's saying, specifically saying hydrogen ion, which is a proton. Okay, and he also defined the base as well. He defined the base is something that contains the hydroxide ion contained. So this is generally like a really useful for the solutions containing the water. In other words, aqueous states, that we believe that HCl aqueous now, NaOH or aqueous, perfectly working, matching that NaCl aqueous plus H2O, liquid like this. Okay, so it works perfectly for those acid and base that contains the hydroxide and some of the hydrogen ions too. And we're still accepting that. Yes, Arrhenius definitions in some like there's some chemical experiments or many cases, because this explains better than many other definitions about like some of the very specific chemical reactions. But the limitation is quite obvious too. First, he was not able to explain the acid and base in gases or like a solid state. It's only limiting in aqueous state. This is remain as his limitations. Yes, obviously we're doing like an experiment quite a lot with the aqueous state, the solution to solutions too, but he was not able to explain why those gas ammonia, for example, NH3 gas is working as a base. Working as a base as in like they have some showing the very specific the indication of the base from the indicators, some other natural indicators, but he was not able to explain why the base is like this is working as a base. Okay, so it's only remains a limitation of the Arrhenius, but there are more. It's also given in here. Failed to recognize that solvent played an important role in the ionization of the acid. Okay, And it doesn't explain why some hydrogen-containing compounds dissociate to give the hydrogen ion in water, while others, such as CH4, do not. So it shares some of the limitations that Davies did. He was not able to explain why the CH4 that contains the hydrogen ion is not working as an acid either. Okay, so we come to the last definition of the acid and base then. That's by two scientists known as Bronsted and Laurie. Some textbooks using Laurie and Bronsted, same thing. Okay, one is a Dutch, one is the English. Okay, so they found the same achievement in the same similar time. Bronsted Laurie definitions, and this is a definition that we commonly use in real day life even now. They found that in like in early like in 1900s, but we're still using. Oh, it's actually like 100 years now. So we're still using that 100 years old like definition even now, because we could not find a better definition than Bronsted Laurie. There are some definitions we use in organic chemistry in acid and base, but you don't really need to know about that now. Okay. Unlike the Arrhenius, they defined the acid as this. They define that acid is something that's doing proton donor. Sounds kind of familiar that we have an oxidation reduction, electron donor, electron acceptor. Okay, so instead of using the electrons, they actually use the proton. That's hydrogen ion again too. They redefine the base is that it's not only limited in the hydroxide. They define that as proton acceptor. So let's bring out the reaction between hydrochloric acid and the sodium hydroxide there. According to the Bronsted Laurie's definitions, they define that as this is working as proton donor, which means this hydrogen will be donated to the sodium hydroxide. According to the Bronsted Laurie's definition, this is working as proton acceptor. Which part of the sodium hydroxide will accept the hydrogen ion? Will be hydroxide part. So what they do, the hydrogen ion comes along, okay, and then will be donated to, and then sodium hydroxide, specifically hydroxide, will accept it, forming the water, H2O liquid, like this. The remainder, the sodium and chloride, will form as we learned, from sodium chloride aqueous. That's a hydrated salt. Does it make sense? So they kind of redefine the end. This is kind of good, kind of perfect to explain that why the ammonia gas is working as a base as well too. So let's have a look at the reaction between ammonia and, let's say, the water. Okay, we have ammonia, NH3. That's a gas, or even the aqueous, doesn't really matter. Put it into the water, H2O liquid. Okay, now what they have found out is this is working as proton acceptor. Okay, and water, as we believe water is a neutral, but water can be divided into the hydrogen ion and hydroxide ion. So this is working as proton donor, which means H2O is now going to kind of split it into the hydrogen ion and hydroxide ion. So H plus comes like it kind of split it and bind it to NH3. As a result of that, what we get is we get NH4 plus, which is known as what? Ammonium ion. The remainder would be hydroxide ion. So now what you see there is we have some ammonium hydroxide, which is a base, according to even for the Arrhenius definitions too. And they actually see that from the experimental result that indicator change the colors, the base, due to the presence of the hydroxide too. Does it kind of make sense? This is how we need to work it onto the proton acceptor, proton donor. And this is why I ask you to memorize some of the acid and base, because that gives you a clue that, acid are simply a proton donor. Bases are simply a proton acceptor. then we will know which is accepting the protons, which is donating the protons to. So that's given in here. So let's go for like an example given here. HCl plus H2O liquid. I did the second part, so you can copy that, the result from this one in here, NH4 plus OH minus. Hydrochloric acid. I just said acid by myself, so it means that this is working as the proton donor. So this will donate the hydrogen ion towards to the water. It becomes like this. As they do so, we're leaving that chloride ion, okay, and leaving some H3O plus aqueous. This is known as hydronium ion. Okay, so hydronium ion is the water that having extra hydrogen ion too. So you may think like, isn't that just the hydrogen? Isn't that just like a hydrogen ion? There is a little difference between hydronium ion to hydrogen. Yes, if you're looking for some net ionic equation, you may need to consider like canceling out chloride on both sides to figure out which is like working as an acid and base. But I like to leave that as hydronium itself for the reactions rather than leaving the hydrogen ion. Okay, so the presence of the hydronium ion, remember that we're coming back to this when we're talking about pH later on too. This is basically equivalent to the hydrogen ion. Does it make sense? So having some portion of the hydronium ion means that we have a same portion of the hydrogen ions too. Because hydronium ion can be easily get split into the water and hydrogen ion as well. I gave the answer for the ammonia that's reacting with the water that's producing the hydroxide ion as it is. Okay, so that is the new definition. I said it's 100 years old definition, but we're still using that now. Okay, but we still sometimes use the Arrhenius definitions because it's better in terms of the explaining hydroxide, in terms of like, especially in the aqueous solution state. And limitation of Bernoulli, we also have that too. Some of the oxide, the base, you remember the oxygens working as a base, they say coming back from the Lavoisier here, they could not explain why does some of the oxides are not able to be going through the acidic reactions. So everything is kind of summarized on the page, I believe page 17, no, page 19 over here for the Arrhenius and the Bernoulli. So please fill up the rest of the table, please, here for the Arrhenius definitions, Bernoulli's base definition, and limitation Arrhenius too. That's page 19 on your workbook. So according to the Arrhenius defined acid as acids ionize or like dissociate. Let's follow that definition given here. Dissociate and produce H plus ions, which is called the hydrogen ions. So I want you to remember the terms called ionize or dissociate because we're going to use that quite a lot in chemistry. So dissociate simply means they are producing or they're making some like involved in the chemical reactions. So according to Arrhenius, acid is defined as it ionizes or dissociate and produce the hydrogen ions. And base is basically the opposite with producing the hydroxide ions. So in between the reaction between acid and base, the products of the acid and base reaction are salt and water. And that's the good definition of the acid and base neutralization. In the same time, also be our limitations. Because it's a limited that is only working only in aqueous states. Okay, some other, and they could not explain the bases without hydroxide. Hydroxide could not be explained either. So the limitation is simply it's only working for the solution to solutions. They could not explain why the gases or like why the solid state could not produce having like same reactions, but Arrhenius could not explain it. And that was kind of overcome by the Bronsted-Lowry's definition. So instead of saying dissociate the hydrogen ion, they defined that as, acids are the proton donors. It doesn't really matter the state, whether that's an aqueous, liquid, or the even solid, as long as they are the one willing to donate the hydrogen, a hydrogen ion, that is the acid. You're right, Ashley? Okay, bases without hydroxide ions could not be explained. Okay, so bases are, according to the Bronsted-Lowry, bases are proton acceptor. So that is a definition, and I want you to remember the limitation of the Bronsted-Lowry too. This is something that is not commonly given in the textbook in the schools, but we had a few cases of the having that trial exam. We have many, like back into like 2017, 16, we have many questions asking you limitation of the Arrhenius, therefore why we need to have the Bronsted-Lowry. Okay, now like one or two schools actually had the question about, hey, what's the limitation of the Bronsted-Lowry, which is not really common, slightly out of the syllabus. But you never know, okay? So it's a limited, it's quite simple too. It could not explain that why the reaction between the acid and acidic oxide and basic oxide could be explained. That's it. That you just need to memorize as a sentence, okay? Means that they could not explain that why oxide that does not have any hydrogens is still working as an acid. And to understand that, you actually need to study a little bit more about organic chemistry later in university. Okay, so even that, like they actually explain that as it can be working as an acid and base in the new definitions. Okay, so those are some definitions we believe now. Remember that. I get rid of those here. Davy, Arrhenius, and Bronsted-Lowry, especially these two, are commonly used. This is what we're accepting nowadays quite a lot. Okay, so let's do some exercise related to those definitions then. In class exercise 1.7, please. Let's do this together. A, considering the reaction between hydrochloric acid and sodium hydroxide, explain the neutralization reaction using Bronsted-Lowry definition. So I kind of did that here. Let's do it again. So we have hydrochloric acid. Let's start writing the chemical reaction between hydrochloric acid reacting with the sodium hydroxide, producing the sodium chloride and water. So first step is you got to explain here that Hydrochloric acid is an acid that donating the hydrogen ion. Sodium hydroxide is an acid acceptor. Sorry, it's a base. It's a base accepting the hydrogen ion. Okay, so when these two are meeting or they're reacting to each other, what happens is hydrochloric acid is it kind of divided into the hydrogen ion plus chloride ion. Okay, from here, from the reaction, hydrogen ion is donated to the sodium hydroxide. Then sodium hydroxide is now accepting that hydrogen ion. Okay, as the hydroxide is the only one that's reacting with the plus. As a sodium hydroxide is basically sodium and hydroxide. If you remember that from the previous on the chapter, the solubility, having the aqueous means that they're being a little bit separated in the hydrated forms too. They're not in solid, they're being like kind of floating. So the hydroxide will be reacting obviously with the hydrogen ion more likely than sodium. It becomes two. Sodium itself left and then leaving that H2O liquid. And then finally, we're coming back to the initial depths. So we don't really write this way. Rather, we just show the hydrogen ion is donated towards the hydroxide ion forming the water as it forms too. Okay, so in forms of the net ionic equations, does anyone remember, like everyone remember net ionic equations? We exclude all the spectator ions, which not really involve in the chemical reactions. We can ignore that chloride and hydroxide. So net ionic equation would be simply hydrogen ion reacting with the hydroxide ion, producing that water. This is the net ionic equation of the acid and base neutralizations then. Okay, but according to Bronsted Laureate, this is something that's very important, that it's not simply they are producing salt in the water. It is actually working as a proton acceptor and proton donor. Okay, question B. Hydrogen chloride gas, and ammonia react to form ammonium chloride solid. Okay, could you write the chemical equations and draw the Lewis structure of this? Been a while, Lewis structure. Okay, for the chemical equations, it'll be HCl gas plus NH3 gas produce ammonium chloride NH4Cl solid. Just follow into the instructions that we have given here. Been a while to drawing the Lewis dot. It's not a Lewis dot, by the way. It's a Lewis structure. So you can show the bonding between the nonmetals in the lines. That hydrogen only has one valence electron, so it forms this. But the chlorine would have the rest of the valence electrons shown as this. Okay, this is reacting with NH3. That is showing that structure of the NH3 with the lone pair on the top. Actually use a different like a symbol for the dot instead. So let's think about what happened according to Bronsted-Lowry. HCl is working as a proton donor. It wants to donate the hydrogen ions, rather when ammonia is working as a like base, accepting that. So what actually happened is this will be divided into hydrogen ion that is just comes as this. Yep. So as the hydrogen atom lost the electrons because of the chloride, now chloride becomes 2 minus with the filled electrons, 1 from the hydrogen like that. Does it make sense? Okay. Now, when this is combined again with the ammonia, it becomes 2. When these comes together, it becomes to this. NH, there will be 4 hydrogens with the extra plus charges. Okay, and then chloride comes along, it simply becomes this. And shows the bonding between ammonium to the chloride, which is known as ionic bonding. A little bit of revisions, but we won't get to many like a Lewis diagram again. That's good to know how to draw that. We probably learned that Lewis diagram last year, this time, year 11, module 1, but been a year. All right, 3. Explain the reaction mechanism in accordance to the Bronsted-Lowry definitions too. So what you have to say is according to is always what you need to start with. Okay, according to, that's 2. According to Bronsted-Lowry definitions, okay, HCl is an acid donating hydrogen ion, and ammonia is a base accepting the hydrogen ion. As a result of that, what happened? As hydrochloric acid donates that, it becomes 2. Just kind of explain that. As hydrochloric acid donates the hydrogen ions, it becomes 2 the chloride as a result. Okay. As the ammonia accepting the hydrogen ion becomes 2 the ammonium ions. And those 2 are forming the ionic bonding as a result. That's all you need to say. Okay, but make sure you start with the according to the Bronsted-Lowry in your first sentence so that it gives you a good definition of the acid and base. And then you can continue on to finish up your answer. Does it make sense to all? Okay, it's not that complicated. I mean, there's a new definitions, but it's quite understandable, I guess. I hope. Okay. All right, compare your answer to A and B and comment on any key differences that you noticed here. So what is the main difference between this reaction on the top, hydrochloric acid, sodium hydroxide, to this, again, hydrochloric acid to the ammonia? It's pretty obvious if you can see like in a state. Yes, this is talking about aqueous states, which is, this is also, this reaction can also be explained by Arrhenius definitions too. What about this one? This is still working, but can you guys notice, did you guys notice that? It does not produce any water, even though this is the acid and base reaction. So again, this is a perfect example of explaining addressing the limitation of the Arrhenius definition, that he was only limited in terms of the aqueous state. It was only limited of the producing the water, whereas this does not produce water at all. Still, it's working as the acid and base according to the Bronsted-Lowry, which means equation B, the reaction to question B can only be explained by Bronsted-Lowry, not by the Arrhenius. Chemical reaction in A can explained by both Arrhenius and Bronsted-Lowry, which gives us clues that why do we accept in the Bronsted-Lowry more and over than Arrhenius nowadays. I hope you see that there's no water remained and the states that is the limitation to Arrhenius again. Okay, we did the 1.8. So let's talk about some more advantages of the Bronsted-Lowry. And we're going to have a break after this, 1.5. Because we are using the proton acceptor, proton donor, and proton acceptor definitions from the Bronsted-Lowry, we are now able to see like some bases and acids. So for example, when hydrochloric acid is reacting with water, so I'm going to take this one in here. Page 20, please. As you can see, hydrochloric acid is working with the water, reacting with the water, okay? And according to, now, I'm not going to use Arrhenius because it's simple. When we're thinking about hydrochloric acid reacting with the water, first of all, Arrhenius could not explain the gaseous state reacting with the water, okay? So this can only be explained by the Bronsted-Lowry definition again. So when hydrochloric acid or hydrogen chloride gas reacting with the water, it produces the hydronium ion with some chloride ions left. In here, as we see there's some difference here, we see that hydrochloric acid, hydrogen chloride gas is working as an acid according to Bronsted-Lowry, which is working as proton donor. Then water is one that's accepting that, working as a base. As a result of that, we get the hydronium ion. Now, I want you to see the difference between, like, relation between H2O liquid and hydronium ion here. Okay, what you see there are only one hydrogen ion difference. That this is accepted hydrogen ion. This is before the accepting the hydrogen ion. Okay, so comparing these two, Joanne, which is working as an acid more likely from these two? Water or which is more willing to donate the hydrogen ion? Hydronium ion or water? This is working as so hydronium ion is working as an acid in these two combinations. Comparing that to, this might be working as a base. This is water. Now, when you see comparing these two, as we can see, like they only have one difference of the hydrogen ion. I call that as those are the conjugate acid and bases. Now, meaning of the conjugate is next to, or thinking about just having one hydrogen difference. So in case of here, we have two pairs of the conjugate acid and base pairs. One is from that, we have hydronium ion and H2O. I'll make sure you write the state. Hydronium ion is the state of the aqueous, water is a liquid. Because it's no longer be a water liquid, it's a solution of the hydronium ions. Okay, this is conjugate acid. This is acid. This would be the conjugate base of that acid. Okay. We also have another one, that hydrochloric acid and chloride. As you can see, they only have one difference of the hydrogen ion. This is working as acid and the base. But I would say that chloride is conjugate base of the hydrochloric acid. I can also say hydrochloric acid is conjugate acid of the chloride ion. Okay, this is how we use the word conjugate in chemistry. It simply means it only has one difference of the hydrogen ion. Make sense, Judy? Okay, next one. We also have ammonia. It's working with, reacting with the water. So what you see from that is ammonia is working as a base, that is working as a proton acceptor. Water is something that donating, which is the hydrogen ion, unlike the previous situation given on the top. Okay, so what happened here is it becomes to the ammonium ion, producing some hydroxide ion there. So from there, we have a conjugate acid and base pairs, which is we have NH4+. That's more like you're working as an acid with conjugate base of the ammonia. So that's acid and base. Does it make sense? Okay. We also have another conjugate acid and base pair, which is we have water is working as a liquid, also working as an acid. That is having conjugate base of the hydroxide ion. It's good to show all the states in your base and as the pairs. That's working as a base. Okay. Now, this is only can be explained using the Bronsted-Lowry's definitions. We can't use the Arrhenius to explain why we get the conjugate acid and base pair. Okay. Now, what you have to focus here is it's about the water. We have this and that. So what you see there is water can be base because it can have the conjugate acid of the hydronium ion. Depends on what it's reacting with. Okay. Water also can also be an acid. Depends on what we're reacting with too. So as we can see from the H2O can be both. Okay, can be both acid and base. In a case that we have a chemical compound that working as an acid and base in the same time, or it has a property of the working as an acid and base, we call that as there are amphiprotic. Does anyone know like amphibians, frogs, for example? They can live under the water, inside the water, as well as on the ground too. So we call the amphibian in that reason too. Amphi means both. It can have like duality. So amphiprotic means that they can accept. Means that can accept, also donate the hydrogen ion. So we call like water is working as water has amphiprotic property that can be working as an acid and base according to Bronsted-Lowry, which means that it can accept the water, it can accept the hydrogen ion, it can also donate the hydrogen ion too. So why we need to know about this? Later on, we're going to talk about the buffer in the later chapter. And it's essential to know about amphiprotic properties to understand our buffer properties too. So let's have a think about here. In class exercise 1.9, identify the conjugate bases for the following acids. Remember that the conjugate means that simply having one hydrogen ion differences. So it's pretty simple. Once you understand the conjugate, meaning of the conjugate, we have a HNO3. Let's write in the pairs like this. HNO3 aqueous. Straight away. Remember that conjugate base means that it's ready to accepting the hydrogen. So which means it having less hydrogen ion than the acid that you have. So it simply means NO3. Make sure to leave the minus aqueous. This is the conjugate base of the nitric acid then. 2. We have H2O is working as an acid. Then having less hydrogen to work as a base, it would be hydroxide ion. Next one, H3O plus, working as an acid, hydronium ion, having one less hydrogen ion, which is working as, which it will be water. Lastly, H2SO4, that's a strong acid, working as an acid, having one less hydrogen ion, work to be a base, it becomes 2, HSO4H, like this. So I hope you see that I do not deduct the, like 2 hydrogens to find the conjugate acid and base. It only be one, just one hydrogen ion differences. What about next one? Identify the conjugate acids for the following acids. Sorry, it should be conjugate following bases, typo. Okay, let's find the basis of those. Sorry, acid of those. So what we have given is hydroxide ion, first of all. Okay. Now, as it's working as a base, now to find the acid, it will be an extra hydrogen ion in it. That would be H2O, liquid. Pretty easy, okay? We have a base of the H2O. Remember that is working as a base, means that an acid must be hydronium ion, H3O plus aqueous. We also have HCO3 working as a base. So for the conjugate acid of that, it would be H2CO3, carbonic acid. Then lastly, SO4, 2 minus sulfate, that have the conjugate acid of HSO4, 2 minus. Is it clear? To find the conjugate acid and base pair, pretty simple, pretty easy. Like, if you get questions about this, like, don't get it wrong, ever. Okay. So it's described about amphiprotic properties too. So page 22 shows that some example of the amphiprotic substances. As I said, like water is a definite example of the amphiprotic, but HCO3 minus can be working as an amphiprotic too, which means it can accept the hydrogen, it can also donate the hydrogen. So to be an amphiprotic, this is something that's very important to remember. They must have at least one hydrogen ion in it. Okay? And it's more likely having some charges except the water. So having some charges. So it's easiest way to think about it is any of those having lost one hydrogen from acid. For example, sulfuric acid, H2SO4. If it lost the one hydrogen, it becomes 2 HSO4 minus. Then this will be the state that it can accept the hydrogen, also can donate the hydrogen too. Same for the phosphoric acid, H2PO4, H3PO4. It can accept and donate the hydrogen as well too. So in this stage over here. Carbonic acid as well. Okay, so it's not really complicated to know what the amphiprotic is. Remember that as a definition that it is always what? They are able to donate and accept the hydrogen ion. That's all about it. And remember that this amphiprotic property can only be explained by Bronsted-Lowry definitions because they are the one that proclaim acid is a proton donor, base is a proton acceptor. So let's have a look at those, okay? Oh, I forgot to talk about this, page 23. And depends on how many protons they can donate. We also name the acid as it can be a monoprotic. Mono means only one. For example, hydrochloric acid, fluoric acid, nitric acid, acetic acid, it only donates 1 protons. Diprotic means it can donate up to 2. Maybe it goes in the order, like they donate 1, and after they donate another 1. Okay, but it happens really quickly, so it seems like they donate 2 in the same time. There could be a triprotic, which is like phosphoric acid, and boric acid is a good example. And write it down, the citric acid here too. Citric acid is known to be an organic triprotic acid. It can donate up to 3. And it's kind of commonly used in the school trial exams that they're giving you citric acid as triprotic, which means when you are balancing the chemical equations of those, you may think about there'll be 3 hydrogen ion comes from that, each of those. So for example, triprotic, I showed you one example of the triprotic reaction. When this is reacting with, say, sodium hydroxide, which is strong base, okay, remember that we have 3 of the hydrogen ion can be donated. Assume that if all of those donated, we need to have 3 of those sodium hydroxide. The reason why I'm teaching you they are mono, di, or tri is it's all related to the balancing your equations later on. And this forms the sodium phosphate, H2 plus 3 water. And this is something that's very important to know. I mean, we've been going through that quite a lot, so I'm not really concerned about this balancing equation anymore too, but don't miss that. There are sometimes you miss out, misread the question there, oh, triprotic, and just did that as monoprotic means that you will get completely different answer. Okay, all right. Let's try some of the, I mean, these are something easy questions, so let's give it about 3 minutes for 1, 2, 3, 4 questions, 5 minutes actually. Okay, 1.10. An acidic solution is formed when hydrogen bromide gas is mixed with the water. Write an equation for this reaction. So pretty easy. So that we have known HBr is gas and H2O is a liquid as a given. And you just need to identify which is working as an acid and base. More likely, HBr is working as a acid than base because it's ready to donate the hydrogen ion. How do we know that? If you realize that, like most of the acids, especially strong acid, made with a combination of hydrogen ion and halogens. Okay, HCl, HBr, HF, because that means that if you think about a little bit of the background there, halogens are known to be the most powerful, the most powerful electronegativity means that they're ready to accept, they're ready to take the electron from the hydrogen ion, which means they're easy to donate the hydrogen ion itself too. Okay, so comparing that to this is working acid and base means that it forms these hydronium ion. As the question indicates that we have acidic solutions. This means acidic. Presence of the hydronium ion in any circumstances means we have some acidic solutions now. And remainder would be bromide, aqueous, as it gets dissolved. Easy. 1.11. That in the following reaction, what are the two acid-base conjugate pairs? So pretty easy to, if you understand like what do you mean by conjugate. Again, conjugate means next to, or just simply having one hydrogen ion differences. We have two pairs. So let's start off from the H2SO4. That is, well, that's a liquid. That should be aqueous. Guys, that should be a typo. I mean, it can't be aqueous, too concentrated. Okay. If this is working as an acid, the base must be HSO4, as is given, minus aqueous. That's working as a conjugate acid and base pair. The second part would be HNO3, even though this is working as an acid. We know we learned it as an acid, but depends on what you're mixing with. It can be actually working as a base. I mean, it's forcefully pushing that to accepting that hydrogen ion. So we're going to talk about strength of the acid and base bit later on too, but means that in this time, HNO3 is your base, not an acid. The actual conjugate acid of that would be H2NO3 plus aqueous. That would be conjugate acid then. Yes, I'll ask you to memorize HNO3 as an acid, but again, if you remember, like it's a metal reaction, mixing up the two different metals, depends on how reactive they are. They can produce some oxidation reduction reactions. Similar things happen between those acids too. Next one, 1.12. Show that the reaction between solutions of the sodium hydroxide and hydrochloric acid is Bronsted-Lowry acid and base reaction. So we've been doing that, 1.12. Sodium hydrochloric acid and sodium hydroxide, aqueous. And just identify that as HCl is a proton donor. Okay, and NaOH is a proton acceptor according to Bronsted-Lowry definitions, so that they produce sodium chloride, kind of spectator ions, and remainder would be water. Okay, all right, 13. Write an equation to show each of the following acting as an acid and base with water. Okay, let's see. First of all, we are given HCO3 minus. So let's go for 1.13. So HCO3 minus aqueous working with the H2O liquid here. Now, how do we know that whether like they're working as an acid and base? You need to see. We actually need to compare the strength of the accepting proton or donating the protons. HCO3 minus and H2O are both known to be amphiprotic. Okay, both of them are amphiprotic, means that both are capable of donating and accepting the hydrogen ions. So in that case, we know that definitely this is working as proton acceptor. We need to show that both of the accepting one is working as an base. So if the HCO3 is working as an acid, means it's ready to donate the hydrogen ion to the water. So that means that it becomes to hydronium ion plus that we also get the CO3 2 carbonate ion forms. This is when this hydrogen carbonate is working as an acid, proton donor. But as we know, this is the amphiprotic, means ready to accept. It can accept. So write it down as H2O liquid. This can also working as the base, so it becomes to H2CO3 carbonic acid, and they're leaving that hydronium ion like this. So some of the reactions you need to show 2 of the reactions, depends on what you have. B, we have HPO4 2 minus, also working with the water. First of all, if this is working as an acid, proton donor, it would donate the proton to the hydrogen ion, so it becomes the hydronium, and leaving that to PO4, 3 minus, aqueous like that. This can also working as a base, that proton acceptor. So when this is accepting the proton, becomes to H2PO4 minus aqueous, then leaving that to OH minus, like this. Again, remember that this is working as an acid. Now this time working as a base, because this is amphiprotic. Next one, HSO4, same thing. Minus should be, yeah. Working as an acid, accepting the hydrogen ion, becomes to hydronium ion, leaving that SO4 2 minus. And we also have H4SO4 aqueous working as a base. That's leaving that H2SO4 and the hydroxide ion. Okay, the last thing. What about water? Water is working with the water. This is something that's very interesting. We probably think like water doesn't really working with the water itself, but they do actually. So what they happen is, if one of those working as an acid, the other one must be working as a base according to the amphiprotic properties of the water. So assume that this is working as an acid, this is working as a base, and proton donor, proton acceptor. Then it becomes like this. We have some hydronium ions are formed, and some hydroxide ions are formed as well too. But this reaction, if you can easily donate the hydrogen ions to each other, this will actually go for the reversible. Becomes the equilibrium as well too. So we're going to talk more about this one. This is why you need to study Module 5 to understand the Module 6 contents. Makes sense up to here? Everyone good? Okay, this is the end of Chapter 1. We're going to do the Chapter 2 as well today. All right, let's go to break. Yep. I would like you to open up chapter 2. Yes, we're going to start chapter 2 as well too. It's like some revision from year 10. You're right. Okay. Some revision from year 10 that we learned about some reaction between acid and bases. Like I probably asked you to memorize some templates. So let's go for some templates of the acid and base reactions. Depends on what kind of acid and base we have. We know that some reactions are quite easy to remember. So for example, when the acids are reacting with the metal hydroxide, they're producing salt and water. Salt as in like the ionic compound. So as like a template too. I'm using a little more about, from this chapter and Arrhenius definitions too, so that give us a better understanding about the chemical reactions too. But in any time, we can also use Bronsted Lowry, the hydrogen ion donor, proton acceptor, proton donor. So let's jump onto the question straight away for the neutralization reactions. From this chapter, yes, you got to deal with quite a lot of the moles and some module 2 that N equals to CV questions a lot. So good revisions. Let's start from 2.1. What volumes of the 0.2 mole solution of the barium hydroxide would be required to neutralize 150 mils of the 0.5 mole solution of nitric acid? This is the question that you can possibly get at school exam to the practice. But first things, always start with balanced chemical equations. Now we know that barium hydroxide is BaOH2 aqueous, barium is 2 plus, hydroxide 1 minus, reacting with nitric acid. I ask you to remember the nitric acid, HNO3, for this reason. Okay, if you remember that, this is the acid and base reaction between acid and hydroxide, forms the barium nitrate as a salt. Plus that, the water, H2O liquid. But to balance this, we need to have a times 2 on the water side here too. After you get the coefficient values right, and then you got to write it down all the relevant information you have given. So you're given that we need to find the volume of the barium hydroxide to neutralize 150 mils of the nitric acid. So let's write it down in here. We are given from the nitric acid side is you're given volume of the nitric acid is 150 mils. That must be converted into liter. That's 0.15 liters straight away. Concentration of the nitric acid, HNO3, is given as 0.15 mole per liter, given as that. Okay, let's write it down. Volume, amount of the concentration of the barium hydroxide as well too. That's given as 0.20 mole per liter too. After you write down all the relevant information, you need to think about how you're going to find the volume. So what you need to think here is about the reaction ratio between barium hydroxide to the nitric acid, that is 1 to 2. Okay, again, which means if I have 1 mole, 1 barium hydroxide, I need to have 2 of the nitric acid to fully reacting without leaving any of those reactants. Make sense? Okay, been a while, and that'd be good revisions. So to do so, we need to find the number of mole of the HNO3 easily by using this CV. Make sure you show the relevant working out like this. Okay, I need formulas for the N. This is then NC 0.15, that times the 0.15, basically square of those 1.15. You get 0.0225 mole is amount of the nitric acid you're given. This amount you're given. Then according to the reaction ratio of the barium hydroxide to nitric acid, which is given as 1 to 2. Okay, again, if we have 1 mole of this, I need to have half of that remains. It's a 1 to 2 ratio. Okay, if I have 2 moles of this, I need to have 1. If I have 1 mole of this, I have a half of that. So N of the barium hydroxide must be half of the N of the HNO3. So divided by that by 2 is you get 0.01125 mole. This is amount of the barium hydroxide is required. Okay, this is required. Therefore, to find the amount of volume, remember that C equals to N over V. Then just write it down, C equals to N over V. V is equals to N over C. So the volume would be then N, which is 0.01125. Then divided by the concentration, that's given as 0.15. Sorry, 0.2 for the barium hydroxide. So that divided by 0.2, you get 0.05625. Now, fix that into the sig figs given. You're given 2 sig figs in here. So this must be then 0.056 mole. Sorry, the volume liter into sig figs. Too easy. Okay, nothing really complicated about this type of questions. Okay, but just make sure you memorize the template of the acid and base reaction. Just simply salt in the water. That's not too complicated. Everyone good? Okay. What about next question? Similar type of questions too. Give it a go. Okay. In chemistry, make sure, I know it's kind of like hectic to write all the working out, but it is relevant, it's required. Try not to skip any of the working out or any relevant information in your working out, please. Make that as your headed. So you need to always focus on how to find the number of moles and matching up the number of moles. Therefore, you can find the relevant answers to that. Easy, okay? All right, after you write the balanced chemical equation, it would be something look like this. The barium hydroxide reacting with sulfuric acid, producing barium sulfate, producing 2 water molecules. All right? Concentration of the sulfuric acid is given as 0.005. Okay.
in your writing down the relevant informations, make sure you include the relevant sig figs too, which is given on your questions. Okay, that's a little like a small tip that you don't forget about writing in the relevant sig figs later on too, because sometimes even though you wrote down, you have to given some sig figs here. Depends on whether you use the value in your calculation or not. You may need to use the different sig figs. In the case of here, you have given 3 sig figs, 3 sig figs, and 3 sig figs, which is good. You can't just need to finalize your answer in the 3 sig figs in this case. I'm talking about when you're giving 1 sig fig values. Yes, I hate to see the 1 sig fig. I had to write your answers in 1 sig figs too, but if that's given in your question, you need to follow it. Yeah, even though I really hate to see the 1 sig fig answer. So, starting from that, N of the H2SO4 is founded by CV, same working out as to that. So that is basically 0.075 times 0.005. And 0.075 times 0.05, you get 0.000375 in mole in the 3 sig fig values given. Okay. This is according to the due to it's a various method you can due to the reaction ratio. The N of the barium hydroxide must be same as N of the H2SO4 straight away, which is same as 0.000375 mole. Got it up to this point? Okay, then you can simply find these. Volume of the barium hydroxide is therefore can be found by N over C. That's 0.000375. Then divided by the concentration they were given. That was 0.100. So that divided by 0.10, and you get 0.00375 mole per liter, 3 sig figs. Units, sig figs, values are included in your working outs. Volume. Oh, sorry about that. Yeah. Liter. Okay, that's how you need to do the deal with these type of questions. Again, it's nothing really complicated here yet. Okay, until we learn about a new calculation called the enthalpy of neutralizations. Yeah. As soon as you see the enthalpy, you'll be like, oh no, not again about enthalpy. I thought it was over. I told you that module 4 is a part of the HSC. You will get lots of questions about enthalpy, entropy gives free energy. And this is something that loved by the examiner. Okay, I make it really simple. Don't worry, like this is I make it really try to make it really straightforward in here. Okay. When we're talking about enthalpy, guys, okay, don't get freaked out about enthalpy. It simply means whether the heat is released or absorbed. It's all about whether we can boil the water or we can cooling down the water. Does it make sense? Okay, so we learned about in module 5 that module 4 too, when delta H is negative, we call that as exothermic reaction. Therefore, it releases the heat to the surrounding. Now, interesting fact about neutralization. I'm talking about acid and base neutralization here. They're known to be an exothermic reaction, just like a combustion. Okay, we learned that combustion is a definite example of the releasing heat exothermic. Neutralization is another example of the exothermic reaction, which means we write that delta H of the neutralization is always be less than 0. It indicates that it's exothermic. That means that release heat to the surrounding. So what that means is you are able to feel the heat, when you just put your hands close to. Okay, just like a combustion reactions do. Now the question simply asking you here is, hey, then let's find out the heat of the neutralization. Just like what we have found the heat of the combustion. Do you remember like how we found the heat of the neutralizations, delta H of the combustions? We usually something like kilometer or we set up the two beakers with the combustion. We have the sprit burner. We boil the water. Okay, we found out the amount of heat increase by finding the amount of the fuels that we used. Okay, so it will be something that very similar, but what we have to focus in here is we need to focus on the neut, which stands for neutralizations. Okay, the neutralization means as a result of the mixing of the acid and base, what we get the water. So neutralization is kind of described, expressed in the amount of H2O produced in acid and base reaction. For example, assume that I have hydrochloric acid, again, reacting with sodium hydroxide, obviously producing sodium chloride and H2O liquid. Now, assume that I only have 1 mole of the hydrochloric acid, but I have 0.5 mole of the sodium hydroxide. Okay, now considering the meaning of the neutralizations and thinking about the chemical reactions, up to 0.5 mole can only be reacting because we don't have more of the sodium hydroxide. So it's kind of obvious. This is your limiting reagent, which means it will only produce 0.5 mole of this water. Does it make sense? The rest of the hydrochloric acid will be remained there and 0.5 will be remained. This would be 0. So can we say, according to the definition of neutralizations, only 0.5 mole of these are neutralized? Does it make sense to all? So we are following to the number of mole of the water to chase it up how much of the neutralization we had going through. Does it make sense? This is why you need to master those balancing equations, find the number of moles in module 2. Okay, so that means, let's think about it here. We don't know the delta H of the neut. We don't know. Okay, but what we know here is this is the exothermic reaction. And how do you find the delta H? If you remember that, delta H is found by, there are various methods. One was Q over N, where the Q stands for the heat divided by number of moles. Now, I'm going to put that for delta H neut specifically, that is a minus Q on N. Okay, because we know that this is an exothermic reaction. This means it's kind of exerting the heat. I'm not going to put the minus on the general equation of delta H because I don't know whether that's exo or endo. Does it make sense? Okay, so can we say this means that minus Q, the heat is generated or exerted from the neutralization reaction divided by the N, number mole of the water. Why am I taking the number of moles of water? Because as I said, we can determine the stance of the neutralization from that number of the moles of the water produced. This is the evidence of the neutralization, pH 7. Does it make sense? Okay, so only for the water. So and then how do you find the Q? This is the main issue. How to find the Q? We can find the Q using, okay, I hope you remember this, MCAT. Yep, the M stands for the mass of the mixture. I'm not saying that M is the mass of the water simply because if you think about it in here, I still remain some 0.5 moles of hydrochloric acid. So it'll be a mixture of the hydrochloric acid and the water. Does it make sense? So I'm not going to take the number mole M of the water straight away. It's M of mixture. C is a specific heat of capacity of the mixture. Okay, now delta T is what? Change in the temperature. Temperature. The unit for the T, does anyone remember that? Unit for the T is Kelvin. Or like, but we can use delta T for we can use degrees Celsius too, because we're taking about the difference between the initial and the final temperature too. All the degrees Celsius, I just write it down here. Specific heat capacity, okay? Remember that specific heat capacity is how much, if they receive that, it's kind of complicated, so I'm going to explain that now. It's about like if they receive certain amount of heat, they can increase the temperature. It's the capacity, how much they can increase. Mass of mixture must be given in the grams in here. Okay, this is given in joules per Kelvin per gram. Now, in the combustions, when we learned that in module 4, we learned that it's 4.18, which is the specific capacity of the water. Because what we've done in the specific in that experiment, we boil the water from the combustion of the fuels. Here, what we do is we mix the acid and base. We seeing that some increase or decrease in temperature using the calorimeter too. Does it make sense? Okay. In that reason that we are able to get the determined delta T. So in many cases, unless this is something that you have to make sure, this is also given. Okay, it's assumption given over here. Unless you are given the value. If you're not given the M and C, because to find the mass of the mixture, you actually need to know the density of the mixture. What we believe is density of the water is 1 gram per milliliter, or 1 kg per 1 liter. Okay, so we kind of take that, if we have 100 grams of the 100 mils of water, we take that as 100 mils. That's what we believed in so. But mixture, as in like hydrochloric acid, would not have the same density as the water. Sometimes you're given the density of that mixture given. That's what happened in 2019-20 HEC examination. That they were given that the density of the sodium hydroxide was a certain value. Okay, if you're given that, you got to use the density to find the extra mass. For example, if the density of the hydrochloric acid is 1.02 grams per milliliter, okay, if you have 100 mils of the hydrochloric acid, this is equivalent to 102 grams, not the 100 grams. Okay, now you do not need to memorize the density of the hydrochloric acid, because what we do is, because every single time we deal with these type of questions, unless you're given those densities, you can use the assumptions given here. Okay, one assumption first, the salt solution formed from the reaction has the same, highlight that please, same specific heat capacity of that of the water. So what we do believe that is, this C is almost like the 4.18 times 10 to the power 3. Let's use the value given in your formula sheets again. Let's get 1.10 to the power 3 joules per kg per Kelvin. Okay, this means same as 4.18 joules per grams per Kelvin too. Okay, we can use that. That's the first assumption, unless you're given actually specific capacity of the mixture. Okay, I tell you, like I show you what question I'm talking about. Why?
Yeah, the top one minus 3.
Which is minus
Times 10.
4.1.
10 to the power minus 3, is it?
But like the
No.
So that's
Joules per kilograms per Kelvin.
Uh-huh.
If we combust we boil the 1 kilo, we require this much of the energy. This is what you give it in the formula sheet. This is why I'm using the one.
Wait, what about the bottom?
Joules per, because we convert it in kilograms to grams.
Okay.
Means, okay, you can think of it this way.
Mm-hmm.
This means that to increase the temperature by 1 Kelvin for 1 kilo of the water, I'll write it down here. It's been a while, I know. Okay. To increase the temperature by 1 Kelvin for 1 kg of water, 1 kilo of water, 4.18 times 10 to the power 3 joules of the energy required. Okay, this is quite a lot of energy, by the way, because we have 1 kilo of water. Now, what we do have the grams, 1 gram, means it takes a less amount of energy, 4.18 joules per kilo. Sometimes, I know that we're using this, 4.18 kilojoules, or saying times 10 to the power minus 3 kilojoules per grams per Kelvin like this. Sometimes we're using 4.18 times 10 to the power of the 3, or 4.18 kilojoules per grams per Kelvin here like this too. Times 10 to, sorry, this is the same unit. Kilojoules per kilograms per Kelvin like this. I know this is something that's very confusing too. This is why I'm gonna stick on to the units we have in the formula sheet. This is something you will be given and you will not get confused about this value. Just use this and just convert the units back into whatever you need to do. Okay, so if you're given, for example, if you're given like 100 grams from the mass of that, convert it into kilograms and matching the unit, which is 10 to the power 3, you will never ever get it wrong. Okay, I mean, there are various methods to memorize this value, but let's stick on to that for now. Okay, unless you feel more familiar using some other values given. So this is the first assumption that we do. Even though we are given some hydrochloric acid left, we still take that as specific heat capacity of the water. Okay, obviously it'll be slightly different too, because if you're boiling the hydrochloric acid, it'll be slightly different to boiling the water. But that's the first assumption. Second, all thermal energy released by the reaction is transferred to the salt solution. There's no energy loss. This is the second assumption that we make. Does it make sense about the second assumptions? Third, if the mass of the salt solution formed was not, then it can be assumed that the salt solution has the same density as the water, which is 1 gram per 1 milliliter, that's SO2. So even though we are left with something as hydrochloric acid left in here, we just take that as the same density as the water. Does it make sense? Okay. So this is the 3 assumptions that we need to make to solve, unless you're given that actual density values too. So what we're going to practice for now is we're going to use those assumptions to take the measurement of the heat of the delta H of the neutralizations. Okay. Remember that delta H is simply measuring the capacity, like how much heat it can be released per mole of the water produced. So please remember that H newts is calculated by Q divided minus Q on H2O, and we put the negative value because we know this is an exothermic reaction. Okay, so let's do some questions related to that. Next page, page 64, please. I'm sure I have some extra neutralizing questions too. All right. 50 mils of the diluted standard sodium hydroxide solution was added to the neutralized 50 mils of the 2 molar solution of the ethanoic acid. The temperature of the mixture rose from 22 degrees to a maximum temperature of the 33.7 degrees. Determine the enthalpy of the neutralization then. Okay, in here, I gotta use all the assumptions that we made. So first assumption is, let's write it down actually. Assume that. Okay, the assumption that we had before. First, the C is 4.18 times 10 to the power 3 joules per kilograms per Kelvin. Okay, and second assumption is the density of the solution is 1 gram per milliliter, just like a water. The third solution, the assumption is there's no energy loss.
You don't have to write it down, this assumption, every single time you're dealing with the questions because you're just not given it in here. But it's good to show that because it gives you some better ideas about how to approach to these type of questions. Once you get the assumption there, start with thinking of balancing chemical equation again. That we have sodium hydroxide, aqueous, reacting with the ethanoic acid that is known to be acetic acid, CH3COOH again, forming that into the sodium acetate, and then leaving that water. What you have to focus here is the reaction ratio between sodium hydroxide and acetic acid, which is 1:1:1:1:1. Okay, which means for the certain amount of this, you produce the 1 mole of the H2O in the same reaction ratio. So what you're given here then is, we're given 50 mils of diluted that is given and neutralized 50 mils. Okay, so you were given N, let's go straight. N of the ethanoic acid can be found by CV, that you're given 50 mils and 2 mole solution there. So 2 times of the concentration times that 50 mil converted into the liter, so 0.05, giving you 0.10 mole is given. The question didn't specify how much of the sodium hydroxide you're given, 50 mils is given. Okay, so it simply means that added to that, assume, okay, and then assume. This means assume all the sodium hydroxide and acetic acid reacted, then N of the H2O must be same as N of the acetic acid we produced. That is 0.10 mole. Okay, because if all of those acetic acids got neutralized, it will produce the same amount of the water according to the reaction ratio. Everyone good up to this point in here? Okay, now the volume, second part, the volume of the mixture, or the volume of the solution is, we have to think about the volume of everything. The volume, first the volume of the sodium hydroxide you're given, plus that the volume of the the acetic acid, which was, you're given 50 mils plus that too, acetic acid of the same amount, 50 mils too. Then 100 mils was given. After we mix the 50 to 50, you get 100 mils. Then the mass of the solution must be that 100 grams. That's equivalent to 0.1 kg. As we made our assumption previously here, the density is same as the water. Everyone good up to this point here? Okay, then once you get it up to this point, you are able to find this. Oh, first of all, we also need to find the delta T is T final minus T initial. That's the final temperature is given at 33.7. Then minus initial temperature to 22, giving you out the 11.7 degrees Celsius or Kelvin. So you're given kg, degrees Celsius, then you can find the Q value using the what? MCAT. Q equals to MCAT. M stands for 0.1 times that 4.18 times 10 to the power of 3. That times that delta T, 11.7. Okay, I converted the unit of the grams into kilograms to matching up the unit of the specific heater capacity that's given on your formula sheet. That's joules per kilograms per Kelvin. Okay, but you may do this in a different way. Just convert that into the grams, calculate in the kilojoules too, because anyways, we need to find the kilojoules. Okay, so this is equivalent to 0.1 times 4.18 times 10 to the power of 3. That times 11.7. You get 489.6 joules. This is equivalent to 4.89.6 kilojoules, as we need to find a delta H unit in the kilojoules per mole. Then delta H of the neutralization is found by Q on N of the water. That is minus 4.8906 kilojoules divided by the water that we given, 0.10 mole. So that divided by 0.1 is basically times that. You get 48 times 48 plus, sorry, dot 906. Given that sig figs of 3, fix that into 3 sig figs. That's a 3 sig figs. Okay, negative kilojoules per mole. So this is the heat of neutralization for this chemical reaction. Does it make sense to all? Okay, to find the heat of neutralization, the delta H of the neutralizations. Just make sure, okay, this is so easy to make some silly mistakes. I know that, because sometimes you forgot about put the negative. Sometimes you forgot about converting unit kilojoules per mole, because that is the standard unit of the delta H. Sometimes you convert the unit to the grams. So unit is something that very, very important you deal with in this type of the questions. Don't lose any mark for those, as this means you need to practice quite a lot of those this type of calculation questions, because they love it. Okay, you may actually do a practical related to the heat of neutralization too. And if you're unlucky, I would say unlucky, you may need to write a report about it. Or you may need to get some scientific skills test related to this too. But make sure you remember that we make the assumption unless you're given some of the values too. Okay, so I would like to try for the next question then, 2.4, the similar type of questions, and I will give you some extra, more of the neutralization question print.
We have to write the assumption.
No, as I wrote the assumption here, you don't really need to. But it's good practice if you can write the assumption every single time you deal with those questions. So this is 2022, 2 years ago, the year before. The question from HSA 26, as you can see, like you actually get some neutralization here, delta H, straight away. But in that case, we assume all the solution. This is giving the assumption. So in the case you're given, like you have the already made assumption in here, you don't really need to write about assumption again. Okay, but there are some cases that they actually use the different values. So to 21 HSA. It wasn't this one. No. No, it wasn't 20. Yep. Okay, somewhat it's a little like slightly different too, but as you can see, like sometimes they're giving you the density values or like some of the different values given, and you need to follow that instructions. So that was for the heat of combustion of the biodiesels. That's using the different density values. That's something that you have to be aware of. Remember, one question was actually really tricky in this here. They're okay. They're okay. Never mind. I will share that once I can. Oh, here you go. You've probably seen the questions because I gave you that in your topic test somewhere before. I showed you some sample questions. Mixing up the sodium hydroxyhydrochloric acid, sodium chloride, and that is produced, which is kind of easy. But if you read the question really carefully, you probably saw that the specific heat capacity resulting is not the 4.08, it's a 3.99. That was given. Okay, and they're also given some density values. The mass of the solution is not the 100 mils, 103 given over here. So that's what I'm talking about. If the question's actually giving you a specific amount of the solution or the specific capacity values, don't make the assumption. You can't make the assumption anymore. Okay, that's the case. That was 2009-20 HSA paper. 23 paper, 22, 23, 24 now. 23 paper was reasonably similar to this type of questions too. So why not for this year? All right. So hope you understand some of the contents. We will have a chance to go through that again. All right, let's finish on 2.4. 25 mils of the diluted standard barium hydroxide solution was added to the neutralized 50 mils of the 1 mole of the solution of the ethanoic acid. Okay, the temperature of the solution rose from 21.3 to 34. So let's start off with the writing down the balanced chemical equations. You're given the barium hydroxide reacting with the ethanoic acid. As you can see, 2, you have to times 2, gives you that barium acetate plus the 2 water. So you can't survive without like memorizing all the anions, the polyatomic, the valencies now, especially in year 12. Now, you have to realize that the reaction ratio is not 1 to 1 to 1 to 1. It's 1 to 2 to 1 to 2, which means you're given the N of, you can find the acetic acid by the CV, that is 50 mils to 1.5, so 1.5 times 50 mils, 0.05, 0.075. Yep, 0.075 mole of the barium acetic acid you're given, which means according to the reaction ratio, you can get that N of the acetic acid must be same as N of the water. that is 0.075 mole. Okay, so this is something that's very important to figure out. That's the first step. Then, mass of the solution. As we're taking the same density of the water, you're given 50 mils to 25 mils. So it'll be 25 plus 50 gives you 75 grams using the density values. You may convert that into kilograms if you like to. Yeah, that's fine. That's the same as 0.075 kg. Okay. Specific capacity, have that as your habit. Write it down, the actual value and the unit. That is 4.18 times 10 to the power of 3 joules per kilograms per Kelvin. Okay. Now, one thing that you can do is you can actually change that to 4.18 times 10 to the power of 3 kilojoules per gram per Kelvin. That's fine. Okay, so these two are actually the same. But if you use the grams, you have to use this unit. If you're using this, you have to use that. Okay, so have some more practice on this, and you will find a way like you're more familiar with. I'm just gonna stick on to the units you're given in your formula sheets. That's because that's minimized the making the silly mistakes. So what you get, delta T is found by T final minus T initial here again too. The final temperature was given at 34. Then minus that 21.3. So 34 minus 21.3, you'd get 12.7 Kelvin or degrees Celsius. Doesn't really matter for that because we are looking for the differences. Do not add the 273 because we are looking for the difference between final and initial. Then Q would be simply MCAT, that is 0.075 kg times 4.18 times 10 to the power 3, that times 12.7. If you do so, put in your calculator. You may get 3981.45 joules. Make sure you convert it into kilojoules. This is 3.981.45 kilojoules then. No dot. All right, then the delta H of the neutralizations, make sure you write the copy N of the minus N of the water. The Q is given as minus 3.98145 divided by amount of the moles, 0.075 here like this. So that divided by 0.0. And you get minus 53.086. Now, fix that into the given sig fix that you're given 3 sig fix and 2. As we use a 2 sig fix in the calculations, and in the calculation in here, you need to follow that sig fix of 2, not the 3. So in this case, 2 sig fix values is minus just 53 kilojoules per mole in 2 sig fix. That's it. Okay, it's not that complicated once you understand, once you have to figure out the problems too. But if you don't really understand the delta H or neutralizations, yeah, it could be quite dreadful. All right, that's the first type of the calculation question you can get. Let's move on to the next type of the chemical equations too. I mean, let's skip that for the metal carbonates. That's a pretty pre-ocean knowledge for now. So I'm gonna stick on to the next part. Page 67, please. Let's talk about acidity and basicity of the solution then. Now, as I talked about a little bit more about MV property of the water, water can be an acid and a base in the same time. So let's write it down, the formulas again. It's given in here, but let's write it in here. So we have a 2 water reacting each other. So I'll probably write in a different color for this one. Let's make it blue, H2O liquid. Okay, and one is, let's say one's working as an acid, one is working as a base. Remember that acid and base in the Bernoulli, proton donor, proton acceptor. This will form, donating the proton to this, formating the H3O. H which is known as hydronium ion. Let's write it under here because I like to put the plus first. Okay, and we can also have the OH minus from the acid part. So we can definitely have some conjugate acid and base pairs, but as we can see from these are the really love to react to each other due to the plus and minus. As I said, this can be reversible like this. Okay, then if we have a reversible reactions, that means we are able to find that it's dynamic equilibrium state. So most of the water that you're drinking, you're having in your water bottle now, they're at the equilibrium state. How do we know it's at the equilibrium state? You didn't see any change in the concentration. You didn't see any change in like colors of the water. You didn't see any difference of the water taste. So that's how we know, indicate that they are reached at the equilibrium as well too. Now, something that we have to know is, in the pure water, in the second dot point please, in the pure water at 25 degrees Celsius, hydronium ion and hydroxide ion concentration are at, let's write it down in here, at 25 degrees Celsius, concentration of the hydronium ion is same as concentration of the hydroxide ion in that given solution. That is 10 to the power 7 minus 7 per mole per liter. Remember that that's in the very specific heat that is at 25. Because what happens is if you increase the temperature, you can alter the amount of the product and the reactant. Okay, but just let's stick on to 25 degrees Celsius for now. So that means for 1 liter, you're having that the N of the H3O plus the same as N of the hydroxide ion at the equilibrium would be 10 to the power 7 mole. Okay, this is the amount of that we have in here. Then let's do this. As we are having some dynamic equilibrium, and we all know that the concentration of the product at the equilibrium too, we are able to find the K value. Okay, the K is known to be what? The product on the reactant. So in this case, we have a product of the hydronium ion times the hydroxide ion. Okay, that divided by the water. However, as you can see, the water, that's a liquid, the pure substances. So we ignore that. Does it make sense? Okay, then using this, the value that are given, you get 10 to the power minus 7 times that 10 to the power minus 7. What is this? That's giving you 10 to the power minus 14, according to indices low. Yep. So I call this is a K, which is the equilibrium constant of the water at the 25 degrees Celsius. And this is what, and the reason, I'm going to put the W, which stands for the water, the equilibrium, so it stands for water. The equilibrium constant of the water at 25 degrees Celsius is 10 to the power minus 14. Does it make sense up to here? Okay. Now, let us think about in this case in here. That's given 10 to the power minus 14 is given at the bottom too. Then we are able to know that here, this is giving you it's a neutralization sized. Simply because we have a certain amount of the same as the concentration of the water is same as the concentration of the hydroxide ion. Okay, then let's think about it here. You're given concentration of the hydronium ion is 10 to the power minus 7 mole. You don't have to write this one yet, okay? As I said before, the hydronium ion, we take the same as, this is same as concentration of the hydrogen ion that we have inside. Because thinking about here, to produce a certain amount of hydronium ion, we need to have a certain amount of the hydrogen ion need to be released. Same amount will be goes in here, okay? I don't like to see that 10 to the power minus 7 every single time to determine the concentration. So what I do is, I'm gonna put some logarithm in here. So what I'm going to do is log 10 of the H3O plus. Okay, and I want to see that negative value, so I'm going to put the negative value here like this. And what you see there is minus log 10 of the 10 to the power minus 7. Now, those of you who learned about indices like logarithms, you know that the power comes to the front of the log, minus cancel out, so you see the 7. Okay, that's a rule of the logarithm. Then, instead of writing this, can I just say this is the same as minus log of the 10 of the hydrogen ion as well too, because we take that these two are the same. I don't like to write these every single time. So what I do, I just make the promise that, hey, let's use the symbol P stands for the minus log 10 to the or something. Okay, this is known as pH then. This is the pH. Now how we find the pH of the water, or in the terms of the calculations. Which means we are able to find the pH, which is indicate what? pH stands for the concentration of the hydronium ion in this case here. That's how we calculate the pH value. This is how we use a pH. The reason why water is pH 7 it's simply because that its water hydronium ion concentration is 10 to the power minus 7. Okay. In the same way, we are able to find the pOH. That would be minus log 10 of the hydroxide ion concentration. In the case of the water that we have, it will be in here, 10 to the power minus 7. It will be same as minus log 10, or the 10 to the power minus 7, giving you 7 SO2. So in conclusion, at 25 degrees Celsius, okay, the pH of the water is 7. pOH of the water is a 7 as well too. Does it make sense up to here? Okay. Now, but let us think about it here. We kind of alter that equilibrium system. So somehow we increase the concentration of OH, decrease that. But in every single time we're dealing with that, we do not really change the total amount inside there, which means when I'm adding these two up, when pH and the pOH together, it'll be simply always be 14 by adding 7 and 7. Okay, this is the golden rules you have to remember in every circumstance, not only for the water, guys, it's also applying for any other solutions too. The sum of the pH and pOH is always be 14. And this is known as the self-ionization of the water. They're using this, given on the page number 68. So what you now see there is greater amount of the H. You see the relationship here. The greater the concentration of the hydrogen ion or the hydronium ion in the given solution means that it's indicated by low pH. Okay, it's also indicated by greater pOH. Why? For example, let's think about compare this value. If the concentration of hydronium ion is 10 to the power minus 1 mole per liter, okay, compare that to the 10 to the power minus 7. This is quite big. This is a huge value, isn't it? Because 10 to the power minus 7 is a negative minus 7 value. It's not negative minus 7. So pH is then, as we know, is a minus log 10 of the hydrogen ion or hydronium ion concentration. That would be 1. So indicates that, pH 1 is more acidic. It's more available, a huge amount of the hydrogen ions available. Okay, then what about pOH? Without looking for like an OH value, you can just find that pOH is known as the sum of the pH and pOH is 14. You can simply 14 minus pH gives you pOH value. So that would be 13. Okay, I know it's kind of ironic that, we are having higher concentration of the hydrogen ions, hydronium ion, but always remember that lower pH, more acidic. As we learned that before, like from the everyday experience too. On the other side means that lower the pH plus value means that the greater the pH and lower the pOH value too. Okay, so a similar method like it to prove in this case. Then why do we need to know about this pH and pOH? Again, this is not only talking about the water molecules too, I'm just proving that how we get the pH and pOH contents that is coming out from the water self-ionizations. And this is kind of explaining you why water is your standard. Pure water is your standard of the pH 7. So we're comparing that. What if we have a greater hydrogen concentration than the water? We kind of defined it as acid and pH lower than 7. So how is the question can be related to like this? Let's have a look at the question 2.9 on page 69, please. If we use 1 millimole of the sodium hydroxide to make 1 liter of the aqueous solution at 25 degrees Celsius, what is the pH of the solution? Let's do this question together then. So let's write it down, all the relevant things. We're given N of the sodium hydroxide is given as 1.0 millimole. Okay, milli means 10 to the power minus 3. So that's same as 1.0 times 10 to the power minus 3 mole. Okay, and we also get the 1 liter, the volume of the sodium hydroxide is given as 1.0 liter. So concentration of sodium hydroxide must be N over V. That's 1.0 times 10 to the power minus 3 divided by 1 gives you 1.0 times 10 to the power minus 3 mole per liter. Okay, what we have to understand about sodium hydroxide is when the sodium hydroxide comes along aqueous, okay, remember that aqueous state. I'm not talking about solid. It means it has already been separated into the sodium and hydroxide ion itself, like this. Okay, that's the meaning of the aqueous, which is quite different to solid. It's hydrated already here, like this. So can we say the concentration of the hydroxide ion is actually same as sodium hydroxide? Yeah, because it's already been hydrated, which is 1.0 times 10 to the power minus 3 mole per liter here, like this. Now, we cannot find the pH directly from the OH concentration. So what we have to do, we have to kind of detour that pOH, find the pOH at first, using the minus log 10 of the OH calculate this. That is minus log 10 of the 10 to the power minus 3, giving you what? 3. Then pH can be found from the pOH value. That is 14 minus pOH. The sum of that is 11. Is the pH of this sodium hydroxide then. Okay, let's do B. We have 100 mils of the nitric acid solution with the pH of the 4.0. We diluted the solution by adding water to get the total volume of 1 liter. What is the pH of the diluted solutions? Okay, I give you some full working out and some shortcut after that. So let's think about the full working out. Let's try to understand what is going on here. One thing is you have a given pH of this solution. The acid is given as 4.0 here, like this. Remember that this is founded by minus log 10 of the hydronium ion concentration. Okay, now, if I ask you to find that concentration of the hydronium ion, the way you can do that is slightly mathematically, or you can just memorize that. It would be 10 to the power minus pH, always. Okay, this is how way we can find the concentration back from the pH, which means this would be 10 to the power minus 4 mole per liter straight away. Does it make sense to all? Okay, remember this. This is something that's very important too. And this is the concentration, and we're given in 100 mils. Now, according to the dilution process, C1, we can do C1V1 equals to C2V2. The new concentration C2 can be found by C1V1 divided by V2 here, like this. Now we're given concentration of the nitric acid 10 to the power minus 4. That times that 100 mils 0.1 in the liter, divided by volume is now in 1 liter, 1. So giving you what? 10 to the power of minus 5 mole per liter here like this. Then you can come back, put it back into the pH calculations, which is minus log 10 of the hydronium ion. Then it'll be simply the 5. So pH will now be increased by 1. This kind of gives a clue that, okay, increase of pH by 1 means that determines decrease in concentration by 10. As you can see, the concentration 10 to the power minus 5, 10 to the power minus 4. It will decrease by the 10-fold. So, which means if I have a 10 to the power minus 7 goes to 10 to the power minus 3, the pH would be 7 and 3 here like that for the concentration of the hydronium ion. Okay? If you cannot really understand the point in here, but I'm kind of proving that how we with diluting the solution can affect the pH value. This is the full working out, which is not so complicated. I'm just using that what we learned in the year 11 again, the dilution equations. Okay, let's try it. Okay. All right, see. Calculate the pH and pOH of the solution in which the concentration hydrogen ion is 0.14. Give your answer to the correct 2 decimal places. And okay, I would like to try for C and D. I give you about 3 minutes to try for both. Okay, see, we have given concentration of the hydronium ion, which is 0.14. question asks you to find the pH and pOH of that. So pH can be found by minus log 10 of that. So minus log 10 of the 0.14 straight away. Okay, put that in your calculator. So log 10, 0.14. Your calculator must be programmed in 10 to log 10 anyway. So you get 0.8538. So given that into sig fig 2 decimal point, this is same as 0.85. And there is no unit for the pH, by the way, because it tells you the logarithm value. Okay, pOH can be found by 14 minus the pH, as the sum of the pH and pOH is 14. The 14 minus 0.85, you get 13.14. Given the second exact values, it'll be like 1.5. Let's follow that value. We have 1.5 for the 2 decimal points. Easy. D. What is the pH and pOH of a 0.05 mole per liter solution of barium hydroxide? Okay, let's think about barium hydroxide first of all. If we have a 1 barium hydroxide in solution itself, it is actually divided into 2. That 1 barium per barium hydroxide, you would have 1 barium and 2 hydroxide, like this. Okay, so if you have a given the concentration of barium hydroxide is 0.005 mole per liter, the actual concentration of the hydroxide itself, due to that they released a 2, it would be 2 times 0.05, giving you 0.010 mole per liter there. Okay, remember that aqueous state, it stands for like they're already been separated, so we have a lot of those available in this case. So pOH can be found by minus log 10 of the OH concentration. That is minus log 10 of the 0.010. Okay, so log 0.01, you'd get 2. Yep. Then pH is simply 14 minus pOH. That is 12. That is the final answer then. Okay, so once you understand like the pH and pOH, it's pretty it's quite understandable. Next week we're going to continue on to chapter 2, finish up the rest of chapter 2 and 3, because I want to start about something terms called the strong and the weak acid. We'll compare that to the diluted and concentrated solutions too. You will be quite confused to understand about terms of the strong and the weak acid, but we have to finish that before we move on to the titration practicals, which is chapter 4, I assume. Any questions? Okay. Homeworks. Okay, I'm posting up all the homeworks on your online, so you can download the resources too, because there are people who are missing out because they went to holiday, whatever reason is. Let me know if you kind of get access to the homework. But for you, come here, I'll give you the printouts of the homeworks. Well, that's it.